Following the SpaceX historic 2026 IPO, details have emerged about orbital data centers in space. SpaceX and space startups like StarCloud and TransCelestial are embarking on a science fiction mega project, the AI-1 satellite. We have already discussed about the Panthalassa, the ocean-based AI data center floating freely in the ocean and generating free energy. Must check out that video also. Its simple concept and absolutely genius technology will blow your mind. Now, just for the context, one standard nuclear power station produces about 1 gigawatt. We would literally need to build up to 100 new nuclear projects just to keep up with AI data centers. But can you actually run a high performance supercomputer in the cold vacuum of space? Or is this just a brilliant marketing for an IPO? Now, first of all, the massive advantage of space is that you get unfiltered direct access to the sun. No atmosphere, no clouds, and absolutely no local permitting battles or land constraints. To make this energy reliable, these data center satellites must fly in a highly specific trajectory called a sun synchronous orbit (SSO), the exact boundary where daytime meets nighttime on Earth. The satellite can maintain constant and uninterrupted exposure to solar energy there. Free, clean power forever. The real engineering challenge is delivering the power and rejecting the waste heat. In fact, Musk revealed the early design specs for the SpaceX AI-1 satellite, and it's an absolute beast. Approximately 1700 kg with a massive 70-meter wingspan. It stands 20-meter high, roughly the size of a professional hockey rink, making it 12 times larger than a standard Starlink V2 Mini. Power capacity engineered for 150 kilowatts of peak power and 120 kilowatts of sustained average compute power. It will use highly advanced solar arrays generating 250 watts per square meter. The 150 kilowatt envelope perfectly matches a state-of-the-art terrestrial NVIDIA GB300 rack packed with 72 high-performance GPUs. Each AI-1 satellite is quite literally an independent AI server rack floating in the orbit. But notice how the architecture changes when you look closely. A standard Starlink satellite is incredibly complex because of its massive phased array and parabolic antennas. But an AI satellite is actually mechanically simpler. It doesn't need those heavy terrestrial broadcasting antennas. It is essentially just a massive solar cell array, a high performance chip basket, and a radiator. But that radiator is where the physics gets incredibly tricky. Because space is just a vacuum, there is no air or water to carry the heat away from the processor via conduction or convection. Evaporative cooling is impossible. Instead, the AI-1 has to rely entirely on a closed-loop radiator panel. A fixed volume of water or coolants run directly over the roaring NVIDIA chips inside the satellite bus, absorbing the heat, pumping it out to the giant double-sided radiator panels, and radiate that energy away in the deep freeze of empty space via infrared radiation. Now, to achieve the necessary heat rejection efficiency, these radiators must run hot around 130 degrees Celsius, delivering roughly 1400 watts of heat rejection per square meter. Designing the lightweight liquid cool loops to function flawlessly for over 5 years without any issue in vacuum is easily one of the greatest engineering hurdles of the decade. But heat is not the only enemy in the orbit. There is an invisible chaotic threat also waiting up there, the cosmic radiation. On Earth, our thick magnetic field and atmosphere shield our electronics from heavy solar particles. But in low Earth orbit, high energy particles regularly impact our spacecrafts. Even if one of these particles strike a delicate semiconductor track on a GPU, it can trigger what is known as single event upset (SU), literally flipping a binary 0 to a 1 or vice versa. In a basic communication satellite, a bit flip might just mean a single pixel glitches out in a video stream for a millisecond. But in an AI neural network calculating millions of weight matrices, a single bit flip can corrupt an entire data training cycle, yielding entirely broken answers. So to make orbital AI computing viable, aerospace architects have to deploy three distinct mitigation strategies. First, error detection and correction. Software algorithms built directly into the memory architecture that constantly scan data packets, catching and healing isolated bit flips in real time. Second, triple modular redundancy (TMR). The system runs the exact same calculation concurrently across three separate GPUs and constantly comparing the outputs. If one GPU returns a corrupted number due to a radiation strike, the system takes a majority vote and uses the identical answer provided by the other two. While highly reliable, it is incredibly expensive because you are burning triple the hardware and power for a single task. And third, the physical shielding, encasing the core server bus in dense radiation blocking materials to prevent high energy cosmic radiation from ever touching the silicon in the first place. Now let's talk about the data logistics. Once your AI satellite is powered, cooled and shielded from the radiation, how do you actually feed it data from the ground and get your answers back? If you are trying to uplink massive terabyte scale datasets from Earth via traditional radio frequencies, you run into brutal bandwidth bottleneck. Because of this, the implementation strategy for orbital computing relies heavily on AI inference rather than the raw heavy model training. Companies like the Singaporean startup Transcelestial are pioneering a concept called the Ring, a constellation of roughly 40 highly specialized satellites orbiting the Earth's equator. Now, because lasers in orbit travel through a pure vacuum, they don't experience atmospheric interference like clouds, rain, or dust. They take the exact same laser technology hidden inside terrestrial fiber optic cables and project it freely across the space. These inter-satellite laser links provide over 1,000 times more bandwidth than traditional radio systems. Every SpaceX AI-1 satellite is designed to support a massive 1 terabyte per second of laser connectivity. And if you are worried about high latency lag, don't be. These constellations operate in low Earth orbit, roughly 600 to 800 kilometers above the surface. Now, thanks to the speed of light, your data is physically only about 3 milliseconds away. The latency is practically imperceptible. Now it's time for the reality check. Does the math work? In late 2025, a space startup, StarCloud, successfully launched StarCloud 1 prototype satellite housing a fully operational Earth-grade NVIDIA H100 GPU, proving silicon can survive the orbit. SpaceX is preparing to manufacture these massive platforms at an unprecedented scale out of their massive facilities in Bastrop, Texas. Managing giant constellations isn't new to them. They have already safely operated over 10,000 Starlink satellites in the orbit. The ultimate fate of orbital data centers comes down to a single question. Does the economic math actually work out? Giant solar arrays, complex liquid-cooled radiators, heavy radiation shielding, and constant rocket launches introduce massive, unprecedented upfront capital costs. Will those multi-billion-dollar launch expenses be offset by saving trillions of dollars in electricity, water, and land infrastructure back on Earth? Right now, the exact economic tipping point remains unknown. But as Earth's energy grid continues to buckle under the weight of AI revolution, it might soon become an absolute necessity. Thanks for watching. Don't forget to like and subscribe, and I will see you in the next video.